here we have bisectors of triangles, and we have three theorems. The first one is the perpendicular bisector theorem. And what is a perpendicular bisector, first of all? Well, it's a line that's perpendicular to another line. So here in this little figure, we can see that FK is perpendicular to GM, right? We know it's perpendicular because it has a little square here, meaning it's a right angle. And that's what perpendicular means. It means that FK forms a right angle with GM. And then we have the second part where we have bisector. And what does bisector mean? It means that FK, if it's a perpendicular bisector, it's perpendicular and forms a 90-degree angle with GM. And it splits GM into two equal segments, namely GK and KM. So that's what a perpendicular bisector is. And so what this theorem is saying is that if you have a point on the perpendicular bisector of a segment, then it's equidistant to the endpoints of the segments. What does that mean? That means in this figure, if FK is the perpendicular bisector of GM, then that means that GK is congruent to KM. Right? That's what the perpendicular bisector theorem lets us say. So if they say, the problem says FK is a perpendicular bisector, then you could know for certain that it forms a 90-degree angle with GM, and you could also know from the perpendicular bisector theorem that GK is congruent to KM. Okay, great. Now, the converse of the perpendicular bisector theorem states that if you have this setup with this triangle, and you're given that GK is congruent to KM, or you somehow find that to be true, that GK is congruent to KM, and you don't know if KF is perpendicular to GM, well, the converse of perpendicular bisector theorem lets us say if GK and KM are congruent, then we can say that KF is a perpendicular bisector and it forms a 90-degree angle with GM via the converse of perpendicular bisector theorem. So that's what these two are about, right? And these two are going to help you solve these kinds of problems. We look at example number 1. It says find the measure of FM. So that's this right side of the triangle, right? Well, how can we do it? Well, we can look at the figure and we can see that GK is congruent to KM and that FK is perpendicular to GM. So FK is, by definition, a perpendicular bisector of GM. And because of that, GK is congruent to KM. Okay, that's great. Now, what we can also say is that from here, we could say that GK, since it's congruent to KM, then that means that this angle GFK is congruent to the angle KFM, right? Because this angle needs to open up GK distance, and this angle up here needs to open up KM distance. And since they're the same distance, and since the angles are opening up the same amount, we can say that GFK is congruent to KFM. All right, maybe I should draw this out. So if that's true, and let's go ahead and put this line here, that these two angles are congruent, and we know that these two angles are right angles, then we can say for certain that this angle here and this angle here are congruent because of the triangle angle sum theorem, right? That's because a triangle's angles add up to 180 degrees. So this angle here is 180 minus 90 minus this angle, right? That's what this angle, the corner is. And so since these two angles are congruent in the two triangles, then that means that this angle is also the same. It's 180 minus 90 minus this angle at the top. So the two base angles of the triangle are congruent. Namely, FGK is congruent to FMK. Okay, so the base angles are congruent. That brings us to the converse isosceles triangle theorem, which says if you got the two base angles congruent, then the sides are congruent. So FG is congruent to FM, right? And so yes, so this is an easy problem. We could just say that FM is equal to 2.8. Okay, great. Now, this example number 2 says that BD is perpendicular bisector of AC. So BD, this horizontal line, is a perpendicular bisector of AC. So since we know that from the perpendicular bisector theorem, we could say that CD is congruent to DA, right? So since CD is congruent to DA, we could just set this expression equal to this expression and solve for x. And that's what this problem is asking us to do. It's asking us to solve for x. All right, great. So knowing that, you should be able to solve these problems here, number 1 and number 2. Right? So why don't you go ahead and do that, and I'll go over the answers to that in the next video.